I appreciate you know, all you, Ernesto, Augusto, and many others. And also I like to say that for many years back, one of my teachers on quantitative genetics was Roland, and a teacher and a friend was José Branco. And not much interaction with Ernesto Paterniani, but he came to see me several times. With José Branco, el cantor de Cururú, right? And Roland was like a teacher on quantitative genetics. So, you know, from many years up to now, in which I have received students from Piracicaba as well as Embrapa, from the University in Rio de Janeiro, Fluminense, from Embrapa, good friends of Flavio Breseguelo in Goiás, and Maria Marta. And I have so many names, you know, Masain, Eveli, Italo, Danilo, Germano, you know, Enrique. So it has been a great pleasure to receive a student from Brazil. And I have so many stories on Roland Benkowski. One of them, I remember that I was in Piracicaba and Roland, there was this game, Brazil-Argentina, for the qualification. I don't remember the World Cup, and Roland said, let's come and watch the game in my house. But I said, okay, yeah, but you know, I don't, you know, I like both, not more Brazil than Argentina. But anyway, at that time, and that game, Argentina was winning 2-0. And Roland was really upset, and he said, I bet, Jose, that you go for Argentina, not for Brazil. And that was so funny because he was really upset about it. But anyway, that was, those were very good time. And also, I should say that Fernando Toledo, a student from Roland, one of the last ones, we have the pleasure. Enzymes to our FLP, ALFLP, then moving not only on genomic, but also on phenomics, because I think that we linking phenomic and genomic is for many years, and we have so many different environmental sensors, and we have images, high throughput phenotyping. So I will talk about this, maybe very superficial perhaps, but I'll like to give you an overall idea on what we are doing, and I hope my time will be okay. The outline is basically the motivation is that the field phenomics and genomics offer opportunity to accelerate breeding, and linking phenomic and genomic remains a huge challenge. Genomic prediction based on single trait, but the problem is that the net genetic merit is based on multiple traits. So we go slowly moving from single trait to multiple trait, single environment to multiple environment. Models and meta, we will go through the GBLAB and the GBLAB by environment interaction with the regression model. We'll go to functional data analysis for the high throughput phenotyping, because I think this is a way to have a more parsimonious approach of the problem. we'll see something on Bayesian multi-trade, multi-environment, and then go to deep learning. We don't go to deep learning just to be fashionable, go to deep learning because, you know, with the Bayesian multi-trade, multi-environment, we get very good prediction, but sometimes it takes a lot of time. That's the only reason why we start doing things in deep learning based on artificial neural network. Accelerating genetic gains in the previous equation, selection intensity, heritability, genetic diversity over the time. So the more we squeeze the time, the better. The foundation of the plant breeds remains the same. I mean, experimental designs and control to plot variability, spatial analysis, model and G by E, based on the correlation among experimental trials, environments, farmers' fields. The population size in multi-environment is important, much more with genomics. Genetic diversity, of course, without genetic diversity, we go anywhere. But also, how do we do with the denominator or years per cycle? Well, we can say genomic base is maybe a good solution, or maybe a good, not solution, but a good action to take. Phenome-based images, ready to use. Double haploids, split breeding greenhouses. I didn't put here pedigree, but the pedigree is a very good source. At least for CIMMYT, we have this for free. And with pedigree, we just assess the additive genetic variants. And if we do that, we are just hit the response to selection right there, right here, right? Using pedigree. Now, using markers also, we hit the response to selection. This is the response to selection. We hit the response to selection right there because we have exactly the additive genetic variants or the genetic variants itself. Doesn't need to be additive only. It might be additive and non-additive, epistatic, and another type of genetics. And genetic environment interaction. Foundation of breeding, we know that the Fisher infinitesimal model U is a linear combination of random variables of K. And K is the number of loci. Adding an A allele adds the fixed quantity A sub K, to the breeding value. And the breeding value is U. It is the additive value of an individual, which can be written as this equation, U, W1, A1, W2, A2, WK, K, for K loci. And W are random indicators, taking the value 0, 1, 2, 0, 0, and 2 are the homozygous, this is the heterozygous. We can use -1, 0, 1, or we can use any other transformation of the value of the marker or of the value of the genotype. Remember that now we can talk about genotype. Before, the foundation and the quantitative genetics was without markers, so they use a terminology to express all these terms. We must assume that in U, the W's are mutually independent, so that means that we have linkage equilibrium among genotypes as K increases. And as K increases, the distribution of U converges to a Gaussian model. But linkage equilibrium, the two linked loci, slow down the rate of conversion. So for you to have a finite mean and a variance, individual loci effect and frequency should become a very large infinitesimal effect model as K goes to infinity. Therefore, we can assume that U, or the net genetic merit of the individual, have a normal multivariate normal distribution with mean mu and variance sigma square U. So this is the foundation of the breeding. This is the Fisher infinitesimal model. And this is what we, of course, you know, if you have a tray with 3 loci, so there are 3 components here, so that's no problem. Life is easier, but for complex loci, this is not very, for complex loci, we are not talking about three factors here. We talk about a large number. Genomic selection, we have a known population, a known phenotypes and genotype population. The seed of this is harvest. So this is the seed where we only use markers here. Then we put together the phenotype and the genotypes here, and we put together with the marker genotype, and we want to predict which one of these. So in phenomic, in a standard conventional breeding, you take this, you plant this in an yield trial in different locations. You have here you have families from here, because you cross one plant with another set of plants here. So you have families. And then, but in genomic selection, you don't plant them. You take the markers and predict these guys here. You know the families, of course, you might know the families here. In the testing, this is a testing. So you select the parents based on what? Well, in the markers and in the phenotype. So you do a sort of regression of the markers and the phenotypes, and you make a prediction of the best parents or the best individuals here, in which you select the parents and plant the parents here. And cross the parents and move like this. So this is, so you don't, in genomic selection, you don't put these guys in the field. So you save time, that's all. Now, if you don't believe in prediction, then never do this. Do your conventional breeding. If you believe in prediction, if you believe that the markers will follow that infinitesimal model of Fisher, then you are in a position to apply genomic selection and believe that genomic selection is a good source of information for predicting these guys here. Okay? But I realize that some breeders, they don't like to predict, they want to see the guys here. If they don't see these guys, they don't believe. Okay, that's fine. No problem with that. We believe that we can predict very well these guys here. Well, not very well. We try to be very well. And then, because we know the markers and we know, because these guys are the progeny of this, you know, so we can predict this in a more or less very well and accuracy manner. So these are the fundamentals of genomic selection. The genomic prediction incorporating G by E, because that was the question we asked ourselves. Well, we by 2008 or 9 or 10, we make predictions of populations, but we couldn't incorporate G by E because we didn't know how to do that. We have an idea, but not do it. So we have one publication with Juan 2012, and then Diego Jarquin 2014, where we say, okay, this is the specific model. This is a phenotypic model with a general mean, the environment, the lines, and the lines by environment interaction, and a residual. How about substituting the environment by the environmental covariables? Because environment 1, 2, 3, 4 doesn't mean anything. Now, if we put environmental covariables and if we see that, you know, that the weather in Piracicaba is quite different than the weather in El Batán, Mexico, I mean, but this has to be reflected in some environmental covariables that are causing some effect on the crop in Piracicaba that are not causing this effect in El Batán Simi. So there are environmental covariables that can characterize this environment. There are genomic covariables that will characterize the lines. Therefore, there is a line by genomic by environment interaction that will characterize the interaction between genomics and environmental covariables. In order to do that, then we need to collect environmental covariables and have each environment measure, maximum temperature, minimum temperature, rainfall, sun radiation, etc., etc. So this is in this particular matrix here, omega, okay? This is in omega. In genomics, we have the G matrix, which is the genomic similarity. And this omega is WW prime, which is environmental similarity. And then we have the interaction between genomics and environment that is being derived as the Hadamard product between the genomics and the environmental covariables with a variance attached to each of these that gives exactly the way we shrinkage the estimates in order to have a good prediction. Therefore, we have the genomic model, which is environment, genomic by environment, but we can have also the pedigree. If we know the genealogy of the plants, we can use the pedigree. And in wheat CIMMYT, we have pedigree since 1990. And this pedigree was never used so far for the breeders. Well, that's okay. We don't complain in biometric and statistic unit. We try to convince the breeders that the pedigree is very important because, like I always said, if you want to predict me, use my brother, use my sister, use my mother, use my father, use my aunt. You must. If you have the data from my brother, my sister, my mom, my dad, my grandma, and you don't use to see how I behave in life, then you are missing information. So the analysis doesn't take care of this very important relationship I have with my family. Therefore, the breeder should use this pedigree as well as genomics. Of course, there is no genomic selection without genomics because the genomics, this G matrix approach the IBD, the identical by descent relationship, whereas the pedigree is only family relationship. So the strategy allows this strategy from Diego Jarquin and follow basically what Juan did in 2012, allows modeling interaction using covariant functions. This is very similar. This model is very similar to the covariant structure emerging quantitative genetic for modeling stages, Okerhan and Kempton. Basically, we borrow information between lines occurs only if the lines have genetics and environmental similarity. This work of the rational model of Jarquin was done while he was with Gustavo de los Campos not in Michigan at that time. Gustavo was in, don't remember who he was, in Louisiana. Now, we make predictions, we have the data. The only thing that we do, we've been doing for years, is just to see how we can predict different traits for different crops. But in order to do that, we have the phenotypic data, but we make the predictions and then we do the correlation between the observed values and the predicted values. So we need to do, because we don't know how is the real prediction, we need to do what we call random cross-validation. So we split the testing set and the training set, we split it. And we say, okay, we like to predict the performance of newly released lines, for example. And we call this the cross-validation one. So we have lines that were released and we don't know their performance. So we want to predict their performance. The performance of newly released lines or lines that we don't know and we want to predict. We don't see, these are the lines, these are the environments, We don't see this line in all the four environments. We don't see these lines in all the four environments. We want to predict the lines in this four environment, this line and this line. How do we predict this? Well, we borrow information from the rest of the lines. We borrow information from the lines that were tested in this environment, right? How we predict the new lines in environment. Also, there is a correlation between environments that will also use that information. This is CV2, which is, well, this is like a sparse testing. We see some lines in some environments and not in other environments. Now, there are many other types of cross-validations that we can do. Huh? We can do many other things, and many other things has been published. We use these two because basically they give us a good idea on what is happening. We might say, well, no, I will predict all the lines in this environment. Sorry, all the lines in this environment. So this is what we call CV0. So we haven't seen any line in this environment. How do we predict this? Well, we assume that there are some environments that are related to this environment. They might not. If there are not, yeah, and if the relationship is negative, then our prediction in E1 will not be very good. But still, we have the relationship between the lines that can help a lot. Okay? And this is a typical first example that Gustavo and Diego published in 2014. This is the model, simple model, genomics, environment, and here are the interactions. This is CV1, this is CV2. You see that CV1 is more accuracy. So both the markers and the environmental covariables, they contribute to prediction accuracy. Are you hear me all right? Hello?
Hello, Crossa?
Are you hear me all right?
Yes.
Okay, sorry. No, I wanted to check this because sometimes, sometimes the internet might not be very stable here. But everything is...
So it's fine, no worries.
All right. Another set that we worked with Paulino on this was in cotton data set. We have only pedigree and we have environmental covariables. You see that the models including G by E, environmental covariables by genomics, and environmental covariables by let's see, this is genomics by environmental covariables and genomics by environment. This adds increase the prediction accuracy for CV1 and CV2. This is with pedigree, you see. When in this particular case, for this cotton data, we didn't have genomics, we have only environmental covariables and pedigree. Okay, so that has been said that we've been doing a lot of work on this G by E and published a lot because I think that the models were very robust and there were very, very interesting in people in knowing the, the prediction of different traits. Then also the wheat breeders of CIMID, as well as maize, they start using the high throughput phenotype massively in north of Mexico, as well as in Africa, in Nairobi, as well as Zimbabwe. So we start working on this high throughput phenotyping data because we thought that that is something that we can add to the already high technology of genomic selection. But here the data is different, and we have reflectance data measure over certain number of wavelengths, or what we say bands, in the certain nanometers of the spectrum light from this particular case is a wheat trial. So each of these curves is a wheat line, each of these. These are the different wavelengths, and this is the reflectance of each of the wheat lines for one particular environment, for one particular moment of the crop. Remember this. This is like a picture that you take on the field. So the thing is that conceptually each curve represents a data. So we assume that each genotype at a given time point and under certain environmental conditions has its own reflectance curve. So it will be interesting to see how do we model this, because we have this for each of the genotypes, for each of the individuals, for each of the wavelengths in each of the environment. And obviously one image is not the same. We are not going to get the same range of the spectrum light from a wheat trial if the wheat trial happens to be in a cloudy day. Well, in a cloudy day, I guess they don't do this, but in more humid day than others, or higher temperature than others, or after a rain or before the rain. So it should be a lot of interaction between this wavelength and the environment, as well as the genomic by the environment. We have this wavelength by environment. So we thought in this, and because, sorry, I'm going back before, but we say, well, let's use a function of this. So we will use the data point is not a point, it's a function of the response of the reflectance. So we start thinking in using functional regression analysis for high throughput phenotyping. Functional regression analysis can be used to develop prediction equations for yield and other traits, and can provide yield predictions with similar, or in some cases higher predictive power than that of conventional regression technique. And functional regression analysis can be integrated into patient model and illustrate the application of the functional regression. But basically, what we were trying to do is just to reduce the number of wavelengths in order to get the number of wavelengths in a more, in a more easy manner to deal with that. So we were thinking on this, and then we said, how about putting together the pedigree or the genomics with high throughput phenotyping, and Oswald and others, they start using the standard genomic by environment interaction, but then put in a functional high throughput phenotyping, and then a functional high throughput by environment interaction, which means this is the wavelength, this is the wavelength by environment interaction. This is the genomics, and this is the genomic by environment interaction. And to try to start trying to link phenomics through the image with genomics through the markers. And so for you more or less to understand what is this high throughput phenotyping or functional regression, you know, in a conventional linear regression, you can use a conventional linear regression and have the summation, the multiple regression of all the wavelength introduced as linear regression covariables. Okay? So we go from 1 up to 250. If you have near infrared NIRS, then you can use the NIRS as linear regression covariable. The problem is that K in this case will go from 1 to maybe 3,000. Then you see, then becomes really a little bit, not messy, because this can be done, but a computed intensity. So, but we use a sort of discrete band. We don't use a continuous band. If we want to use a continuous band, we don't use the number of bands. We use the approach continuous function of the nanometers, going from 400 to 800. But now for the conventional linear, then we have this summation of this. Therefore, we can, if beta sub k is the beta regression coefficient for the kth band, this will be estimated in the genomic model. This is the genomic model, you know, plus the effect of these covariables that go from 1 to 250. Now, if we want to use, these are for the discrete case. If we want to use a continuous case, then we need to get the integral from 500 nanometers to 900 nanometers, assuming there is a continuous. Therefore, we have a functional, this is a functional predictor, X sub ij, for the K nanometers or band. And this is the predictor. And this is the X predictor, and beta is the beta functional coefficient. In this context, the integral of the product replaces the sum of the product in the conventional linear regression. Now, the thing here is that mathematically we need to reduce this number, so we use what is called basis function. You know, if you look at, and I'm sorry, I will go back. If you look at these lines here, you see that though we don't have a clear trend, but if you see a spline or a smooth curve, you see that we might use a smooth function to smooth this response to selection. And this is what basically we are doing in here. We use a basis function, which might be a spline, a beta spline, or a Fourier series, to smooth this function. And you see that Ari Vervilla in 1999, as well as Wellham recently, 2007, I guess. But basically, Ari Vervilla from CSIRO, from the statistics unit of CSIRO, they put forward this functional regression analysis, and this is basically that we have based our research for using a basis function to have a more parsimonious model to this. But anyway, this is a functional regression that we use in image analysis. What we have done is assessing the wavelength by environment interaction using model 9 to 14. What do we have here? These are the different time points, which is the different times of the fly of the drone or the airplane. These are the models. The models are going from the standard ELG model to a more sophisticated model that consider wavelength by environment interaction. These are the three environments we have: drought irrigated and reduced irrigated. So you see that when we have a little bit more complex model, using the weight by environment interaction and using a B-spline or a Fourier spline, we increase the prediction accuracy, not much, but going like 0.3 to 0.4 is something. And have this at time point 2, which is very early in the crop, is still better because we save some time. Now, you might say, why you do all this if you are going to harvest the plant anyway? Well, but you can at time point 2, you can already take, if you are going to do genomic selection, you can already take the plants and do the DNA extraction and advance perhaps 2 months or 3 months the crop, and run to the DNA, make selections, and plant the parents, make the crosses, and go to the next cycle. That's the way I see it. There might be other things, other advantages of doing that, but some people say, why all this trouble to if you will harvest a trial? I said, well, it's not a trouble. This is done by the computer once we have the model anyway. Other model that we have used was by Margaret Krauss. Margaret was a student at that time in the WIT program. And he said, well, we suggested this in Montesinos 2016. Use the sequence, the hyperspectral reflectance matrix, and develop a hyperspectral reflectance-based relationship matrix using the S are the bands. S is a metric of center and standardized average of the hyperspectral reflectance. And N bands is the number of bands. This is basically similar to the GBLAP. In the G, we have the markers here, but in the H, we have the bands. Now, unlike G and A, which have only one row and column for each unique genotype, H has row and column for each unique site-year combination, right? Because this is H is phenotype. This is not genotype. This is phenotype. This is phenomics. So we have this for each environment. So Margaret, we suggested to Margaret to fit 2 models. One, hyperspectral reflectance main effect, only the H. And the other model is hyperspectral by environment interaction. So we say, let's model the hyperspectral by environment interaction because then we can do the genomics, the main effect of the hyperspectral, and the hyperspectral by environment interaction. And have this and try this into the models with pedigree and genomics and see if by modeling this hyperspectral by environment interaction, we can gain some over the genomic model. Another way to increase the prediction accuracy and the linking between genotype and phenotype. And these are the results. I don't know if you see that. You see the different colors are the different growth stage of the plant: vegetative, green, heading, yellow, grain filling, brown, and the other one is all together. But if you can see this, if you can turn your head a little bit down, this is the model with genomics only. This is the model with the pedigree only. This is the model with genomics and genomic by environment interaction. This is the model of additive by the pedigree by pedigree interaction. This is the model with the hyperspectral reflectance on the vegetative stage. And this is the model with the genomics and the high throughput and the hyperspectral refractance by environment interaction and the interaction between the pedigree and the environment. This one here. This is the same, but for heading time. This is the same for grain filling, and this is for all. But what I like to show here that might be a little bit complicated. This is for one environment, moderate drought. This is for severe drought, and this is for heat. And you see that most of the time, when at least for moderate drought, when you include the hyperspectral by environment interaction and the genomic by environment interaction, you increase the prediction accuracy. So modeling G by E, modeling the hyperspectral by environment is always a positive response in that. And you can see perhaps not under severe drought environment, sorry, because severe drought is severe drought. You know, in severe drought, sometimes the differences are not very clear. But under heat, you see also differences that always or most of the time when you for genomic-based prediction. We have 8-site year combination for and other things, green light, red light. And we have 2 types of material adapted because we didn't have the data from GBI. This is for CV1, this is for CV2. These are the predictions for each of these traits. This is for CV2. These are the predictions for this trait. You see that when you have G by the wavelength, you increase the prediction accuracy in general. Not much here. But not much for heading, days to maturity, for plant height. Well, not for plant height, but for grain yield, we got this. We were surprised by getting this accuracy of grain yield 0.7, 0.8. I guess we did the analysis like 10 times and we obtained the same answer. So, but in general, we increase the prediction when we put the genomics and phenomics. So we can link this. These are the same, but this was using a wavelength functional regression. This was doing, I guess this was the G block only for CV1 and CV2 for the 2 trails in adapted and exotic. Still, the predictions are very high, especially for CV2, not that much for CV1. For CV2, well, yeah, for CV2, but not that much for CV1. Remember that I said, well, CV1 is more difficult prediction than CV2. So this is for linking a multi-trait, linking genomics and phenomena. Why multi-trait and multi-environment? Why deep learning, multi-trait, multi-environment? Well, because we, these are 2 results, real results of rapid cycling genomic selection in CMID maize for grain yield. This is a publication from José. This is a publication for Zhang. This is A biparental populations. You see that cycle 0 is 2.2, cycle 3 is 2.5. There is a clear increase in prediction. I mean, in genetic gains. These are the mean of A biparental populations. But José was able to do 3 cycles in 1 year. José in Mexico with multi-parental population was able to do 2 cycles in 1 year, but still the increase in genomic selection is very clear. Well, but this is multi-parental population, this is biparental. So this has been done already, and the thing is that the breeders, Joseph, Mange in Africa, as well as the breeders in Mexico, maize, they say, why only one trait? Why not multi-trait? That's the reason why we start looking at multi-trait. These are other results that especially has been published by Joseph, where we have managed, 2 environments, managed drought, optimal conditions. They have 200 hybrids from genomic selection, 200 hybrids from phenotypic selection, 6 commercial checks. And then they put the selections based on genomic, the selection based on phenotypic, and they put it in a field, and they see no differences of the selections based in genomics with respect to basic phenotype. These are the mean. These are the mean of the top 10%. Clearly, these are the commercial checks. This is the guys from the genomic selection. These are the guys from the phenotypic selection. This was a very important result. Very, very clean, simple experiment. And this is what we always said in biometric. You do one experiment like this. Do one experiment like this. Take the selection from genomic, take the selection of phenotype and put it in the field and see which one. The same with José. He had a large number of lines in the training population, in the prediction, and he had white and yellow maize. White phenotypic selection, white genomic selection, yellow phenotypic selection, yellow genomic selection, and yellow and white phenotypic, yellow and white genomics. And you see there are not much differences between the lines selected by genomics and those selected by phenotype. And these are for the top 10%. There are no much difference on that. Of course, these take time, but I think in maize they have done it. So in maize they have advanced a lot in these simple matters of genomic selection, and to reaffirm the breeder that markers and genomics works all right. This is for wheat, where we have genomic prediction, but the correlations based on genomic. In genomic, the correlation based on phenotypic. You see that for all these sites in South Asia, Faisalabad, Pakistan, Bangladesh, Jabalpur, India, Oregon, Mexico, when you have the correlation based on genomic, we increase a lot the accuracy of the prediction or the correlation as compared with the phenotypic correlation. So it's not only what you see in the field, it's also what you add to your phenotypic correlation to have more information as a pedigree and the mark. I show this because I didn't show anything in wheat, and yeah, we cannot show much in wheat because we have done a lot of work in wheat, but still is not fully used the power of genomic selection. Therefore, we say, well, let's try to do this multi-trait, multi-environment. And we start talking to Osvaldo Montesinos, at that time was in CIMIT, with Fernando, and try to start doing some programming to put a model, the Bayesian multi-trait, multi-environment model, that will allow us to have this sort of prediction multi-trait, multi-environment. So this is the model. The beta includes a trait by environment, the beta 1 includes a trait by genotype, and the beta 2 includes a trait by genotype by environment in a Bayesian framework. It's a very good model. It is Bayesian, so it takes some time. But the results, one of the results we have is we say, well, it should be, if we have a Bayesian multitrade environment, we should be able to exploit this relationship between the data much more than using only one single trait. And this is clear for some of the traits. This is green and DBI in environment 1, environment 2, environment 3, days to heading, grain yield, and everything. This is the average across all traits. This is the average across all traits. This is single trait, single environment. This is multi-trait, multi-environment. There's always a possibility of learning how to use this information. Because we have this slow performance of Bayesian multi-trait, we start thinking in using artificial neural network, inspired on the way the modern artificial neural network on the biology works, on the biology brains, and how they respond to external signal and how they transmit this to another neuron, and see if we can learn something from here to do this, all this transformation and have the output here. These are the markers. This might be the phenotypic data, and this is one output, one transformation, and then another transformation. Talking about an easy way to see all these schemes. So we have a single trait. This is for a single trait artificial neural network, where we have the input. These are all the markers. Then we have this hidden layer here, and then we have the output here. You see that there are one transformation here from here to here. This is a regression. We need to estimate these weights here. And then there is another regression, another transformation from this to here. That this is nonlinear, maybe nonlinear, and then the output here. So we can have the red is the input for the blue. Now, multi-trait deep learning is exactly the same as before, but we have, instead of having one layer here, we have another layer. So this is the input, this is the input, output, input, output, input, output. Oh, what did I do? Okay. So we have more transformations, and we estimate the weights here, here, here. There's a lot of transformation going on, because this is the net input and output for the first hidden layer. Here. And the output of this is the input for this, and the output for this is the input to that. And G1, G2, G3 are called activation functions, and are the ones that are causing this nonlinear transformation that we have. So this activation function, they play a very important role. We use an activation function that is called ReLU, which is linear for continuous phenotype. But then we found out that in a sigmoid, in a softmax, we can use binary and ordinal variables. If we mix linear sigmoid and softmax, we have continuous binary and ordinal. So we have the possibility of mixing different type of variables or traits to have one output function for each of the traits. The problem is that there are so many hyperparameters, so many layers. We don't know the number of epochs. We don't know exactly the type of regularization method. We don't know the type of activation function. So we need to tune the model very, very precise, and that might take some time. You know, I was reading some medicine papers where they say that when they have very big data set from cancer. They take a couple of months to tune in the model for the machine to learn from the data. These are some of the results we have. This is for a single continuous trait, like Grenier, deep learning, GBLAP, G/E, no G/E. These are the maize data and wheat data. We have an environment with lines from Iran, with lines from Mexico. And you see that when we include in the model G/E, the GBLAP is much better than the deep learning. Well, when we do not structure the data and don't put G/E, then apparently the deep learning learns that. It learns the structure of the data. Therefore, we get very good prediction for a deep learning without structuring the data, okay? Multi-environment genomics, continuous multi-trait. This is for a continuous multi-trait. It was Grenier and I don't remember the other trait, sorry, but that was something like flowering for maturity. Again, when we put the G/E, the Bayesian multi-trait multi-environment is better than the multi-trait Billion model. When we don't add this structure, the machine seems to learn this and have better prediction than the Bayesian multi-trait multi-environment. Conclusion? Well, the genomics and image data can be put together. Genomics image analysis using hyperspectral increased prediction accuracy. Bayesian multi-trait is a very good model. Takes some time. Bayesian Monte Carlo Markov change sometimes is slow. Multi-trait deep learning are very promising. And I think that we need to do more research on this deep learning neural network. Several deep and signal neural networks are just nonlinear generalized models. I have 3 more slides to show you how some of the students from USP in CIMIT, DSU, they have done it when they come to CIMIT, to get something done. This was a work done by Masaine when she came with Evelyn to do some work in genomics. And you see that, for example, at that time we used 2 kernels, the Gaussian kernels and the Gaussian kernel and the GBLAP. And you see there is always an increase on the Gaussian kernel over the GBLAP for this particular trait and for each of these environments. These are other models that we use with G/E, but also we see a general trend of the Gaussian kernel being superior than the non-Gaussian kernel of the GBLAP. This was a very good paper written by Masaine when she was here in DSU. The same one with Italo. Italo Granato was the only student that came, and the day after he was talking Spanish. He was living with a friend that apparently it was a long weekend talking Spanish. On Monday he was talking Italo, was talking Spanish. But apart from that, he did very good. He developed this BGG environment, new package, and working together with Jaime Cuevas. He visited Jaime that is in Chetumal and published this very good paper where he uses different models with different kernels and so forth, and show that some of the kernels are good. And finally, I arrived to CIMIT 1 week before the pandemic. Germano Costa, he came to CIMIT. And so I saw Germano 1 week, and then I had to come home. And then I talked to him every day for, I don't know, for 3-4 months. Then he finally got a plane to come back to Brazil. But during this time, he was very, very productive. So we just published this paper. where he shows that he has envirotyping on these two data sets. This is the additive and dominance. He has this dialect, additive and dominance, and G by E, and environmental covariables. These are the variances. You see that the variances are high for some of the components, for some of the additive and dominance component, and for the G by E. These are the regression model. These are the prediction accuracies of the regression model. You see that the best regression model was the one that has the blue one with the Gaussian kernel. Sorry. With the Gaussian kernel for the different environments. So this is, we just published this paper because I think that this is a very good paper. Well, we have, he had a lot of data and he was able to put all this data together and make sense of a very good analysis. So with this, and I thank you all the collaborations, because apart from the work we have in the biometric statistics unit with Juan Fernando and Angela and Gregorio, we have Paulino as a consultant and others, and Jaime, and myself. I am the new postdoc in the biometric unit. And and also we have project with Norway universities, with Graminur. I work also as a professor at the postgraduate in Mexico. We have, of course, all the collaboration with the students from the Department of Genetics of Piracicaba, the Colima where Osval is, the University of Guadalajara, where Abelardo is, with Davis in Nebraska, with Michigan, with Gustavo and Marcos, with Quintana Roo, near to Cancun, where Jaime is. I don't know if Jaime works in Cancun or where, but he is a hard worker. University of Wisconsin, we talk a lot with Daniel Gianola, and Cornell University has so many projects when we start all these genomics, and certainly the acknowledgement of all the donors. So with this, I think that I pass a little bit my time, but if you have any question or comments, I'm happy to answer.
Thank you, Dr. Crossa, for
English
your...
or Spanish?
Can be either. Thank you, Dr. Cross, for your excellent lecture, and again for arrange at 1 hour in your busy calendar to stay with us in this Friday afternoon. Now, guys, feel free to make questions. You can use both. Can be open your microphone or typing on the chat. Feel free to make questions. Take advantage of this opportunity. So, Crossa, meanwhile, I would like to make a question for you. Over the last 19 years, we had some waves in genome selection, base alphabet, G by E, machine learning, high-throughput phenotyping, training set compositions. Among this good number of ways, which factors do you think that really increase the accuracy?
It's the way you design the training for the testing. I guess this is one of the main things. Apart from heritability, let's say we have a trait heritability of medium size, right? Like 0.3, 0.4, like talking about a complex trait. I think that the way you define the training population is very important, because you know, there are, so far I don't know if there is any clear rule for doing that. The only thing that we say is, well, find something find something related to the progeny, right? If you don't have anything related to the progeny, then you don't get anything done. But if you have some relationship, then you have. The problem is that sometimes it's difficult when you have a large training population. There are some things that has been, the ESALQ has proposed something.
Mm-hmm.
I think this is okay, but sometimes it's more, how do I say? It's not very concrete the way to do it. I know that Gustavo has done some work on that, on how to select the training for certain testing, but I think that one of the key issues is there.
Mm-hmm.
In any clear way to do it, to me.
Interesting.
Because I give you this example. We have 60,000 lines historically, to predict new 10,000 lines. Mm-hmm. We cannot overpass 0.3 prediction accuracy, 0.4 at the maximum. And we have a training of 50,000 individuals. So the model also plays a role because we have found that by using a non-linear kernel, we can improve a little bit the prediction. How much is difficult to say, but at least 2% we can improve prediction because, and the markers and the quality of the markers. Because when we started this, the prediction was like 0.2, and now we are almost at the 0.4 after 5 years. And I think that the quality of the marker is important as well.
Perfect. Thank you, Crossa. Questions? Someone would like to make any questions? Feel free, guys. You can open your microphone or type in chat.
Roberto, I may ask some questions. Crossa, thank you very much for your presentation. It was really very nice. I'm not very familiar with all these prediction methods, but I find fantastic. So I'm working on a different front. I'm trying to understand the phenotype based on the metabolites and the proteins that an organism has. And from your prediction curves, from your prediction models, do you think that if we include changes in metabolites, changes in proteins, that would help to define, to improve the methods of prediction? Because today we have very nice systems which can provide a huge amount of information on metabolites and proteins and in the thousands. And do you think this would be able to, or would help to improve the prediction methods?
Absolutely, yes. We need to find a way to include it into the model, which will be something related. Some people say, well, this is omics, right? I don't know if
it's omics.
Yeah, it's omics. I have seen presentations where they show very good increase in prediction by using omic data. And I don't know what omic data, but for example, some pathways that we don't know, because, at the end of the day, you say, but what are the markers? Well, that's a different story. We don't know what are the markers. We use all the markers. But yes, but I would say yes. I will agree with that. I think that we can find ways to incorporate the omics data in a very intelligent and useful manner. I have no doubt about it. under deep learning, under artificial neural network, because deep learning is a part of artificial neural network. I think that I think that more and more all these technologies, especially envirotyping, environmental sensors, remote sensing, satellite data, and all the data that we can find on the environments, including soil type, they will help to make a better prediction. Of course, as we improve this, the human deteriorate the environment, and the environment happen the climate change, and predicting 1 year from another one is more and more and more difficult. And this is something that we see every year, right? Every year we see that things are changing, quite drastic. This was a complete unusual year, at least for the summer in Mexico, in the Mexican Valley. It was completely unusual. You see fire in California and Oregon that were completely unusual. So sometimes this will increase the uncertainty that we try to minimize when we do it. But the only data, absolutely yes. Absolutely.
Another question I want to make to you is for perennial crops, how do we apply these prediction methods? I mean, you have several years to analyze the behavior of the plant, the performance of the plant, crop performance. Do you think we can use the same kind of approach to make predictions for, say, eucalyptus, for instance? Eucalyptus in Brazil, we harvest every 7 years.
Yeah.
And the wood quality is one of the points that we are interested in selecting. So do you think that we can apply the same methodologies to?
Oh yeah, that's exactly. And for forest, I think that you can cut the number of years in eucalyptus. You see,
yes,
you see the papers of Resendes, and you see one paper from Felipe. Felipe, what's the name of Felipe? That the guy that is from you guys, but is with Gustavo de los Campos. They show a very good paper on the plant genome, how we can really increase genetic gains and by decreasing the cycle of eucalyptus and by doing genomics. And they take phenotypic data from the greenhouses and use markers and
make predictions.
They really decrease the number of years to half. 16 to 8 or to 7. Big changes.
Yeah.
Increasing
It's Felipe Couto, a former student of my lab.
Yeah, Felipe. Felipe Couto, yeah. Very, very good paper. I think it's a very good example to do that. For example, here in CIMID, we have done some predictions from the bank, using the banks for MLN disease in Africa. MLN disease is a virus, right? It's a virus. Where we predict 20,000 accessions from the bank using 1,000 accessions that were phenotype and genotype, and where we selected the best 200 and the lowest 200, and based on that we predict 22,000, and we got very good prediction accuracy and very good results of the tolerance and resistance to these 22,000 unknown maize accessions and were stored in the gene bank of maize. So for the pre-breeding as well, and I think that Fernando, if he's still here, I don't know if he's in the seminar, I think that he has worked on that, Fernando Toledo. That is also a very powerful tool for accelerating, because the pre-breeding is very tedious, you know. If you enter to CIMMYT, in the CIMMYT entrance, and if you are a maize breeder and you see all these maize of 2 meters tall, you get a really panic attack if you are a maize breeder, because the guys, they just look at the other side of the row and they don't see that, because they say, how do I do here? But these are the gene banks accession. So they need, the pre-breeders need a lot of work to move this to a decent gene pool that will be taken by the breeders. That is, again, you speed up the process, as you mentioned in Eucalyptus.
Crossa, due to this, you have time for just one more question. We have one on chat. Leandro Mendonça asked you about how do you see genome selection in 10 or 20 years? Maybe major using in neural networks, or do you believe that GBLUB or frequentist approaches will keep strong than other statistical approaches?
Yeah, I think that still GBLUB is very useful. And you can interpret that. If you ask me, what is interpretation of neural network? I said, I don't know, I have no idea. Because there are so many transformations there that is but I think in the future we will see much more use of these technologies than now. There is no other way. I mean, you know, the observation of the breeder is fundamental. Right? There is no question on that. I say that very clear because sometimes if a breeder that doesn't like genomics will say, no, this guy is, but you need to use the technology, and one of the technology is using the pedigree. The other one is the genomic. The other one is high throughput phenotyping. We need to use that to enrich our observations. So now I think that deep learning or machine learning in general and deep learning in particular, they have a huge, they will contribute a huge to the breeding, because these are machines that are learning from the data. Therefore, the better the data, the better the learning, right? It's like having a good teacher. If you have a good teacher, you will learn much more than if you have a bad teacher. So that's exactly the same. If you have a good data, the learning machine will learn more and will give results much more precise, and you will be helped by the machine and by the data that you collected in the field or in the greenhouse or in the satellite or in the soil or in whatever other data you have. I think that more and more data will be available, and our decisions will be much more wise. You know, the same as computing simulation. I think the computing simulation should help a lot in giving us something that we don't know based on real data. And then the computer simulation will help us to guide us in something that we now don't know. So all these sort of machine learning technologies will help the breeders. So the breeding will be similar, but much more intense of using data as it is now. And more intense of the quality of the phenotypic data. And much more intense of the quality of the environmental data to assess the environmental variables. And
thank you, Crossa. I think we need to stop here due to the time, but I would like to thank you again in the name of the grad course of Genetics and Plant Breeding, and also the Department of Genetics. Thanks for sharing your knowledge. Thanks for sharing your time with us.
Well, thank you. And I wish you the best.
Okay. You too. So guys, see you again next week when you have the seminar of Germano. Have a good weekend.